So, final swinging bar problem. What's going on at the pivot? And we're going to look at this at three positions. We're going to look at it at its initial position here, at the vertical position, and at that intermediary position. Now, by the way, you've done the textbook problem now. The initial position doesn't have to be here. I can start the bar like that, at any position. This is just for sake of argument to have a consistent set of things to talk about. So, we said that the force of gravity is acting here on the center of mass. Now, how do I know that there's a force at the pivot? Well, I know there's a force at the pivot because the bar is not just falling downwards, right? If this bar was moving or accelerating downwards at g, there would be no force there. But because there's a force there, the bar is not going to move down at g. So let's think about what's happening here if I care about pivot forces. If I care about pivot forces, I really have to start caring about Newton's second law for translation. Sum of the forces is equal to ma, because that's going to help me interact forces with forces. I can't be dealing with torques here because that's not going to help me with the forces. So what is really going on with this equation? Well, something we didn't say before, but it's really important to say now, that this A here always, when you're talking about Newton's second law, is about the center of mass, right? The acceleration of the center of mass is what is important when talking about Newton's second law. So the next thing we have to think about is the fact that all the points here are moving in a circular path, because that's going to become important when we start talking about axes, because it's going to be really, really tempting to want to use x and y axes here. But that's going to be not the way to think about it. What we're going to want to think about is not x and y axis, but a radial axis and a tangential axis, because we showed that this point is accelerating along the tangent. This point is accelerating along the tangent. This point is accelerating along the tangent. And because these points are moving in curved paths, what other acceleration must they be experiencing? And if you said a radial acceleration specifically is centripetal acceleration, you're correct. And so every time we're doing a swinging bar problem and talking about pivot forces, we have to assume that we need to deal not with x and y axes, but with r and theta axes. Now, or r and t axes, if you want to call them that way. Now, here, the radial axis lines up with the x-axis, and the y-axis lines up with the tangential axis. But we don't want to get suckered into that. The textbook is going to try and sucker you into that and try and make you think only about x and y. But if you think about r and theta and then translate into x and y later, you're actually going to put yourself in a good stead. So what's going on here? Well, every time we have a pivot, what we're going to do is we're just going to take a guess at what direction the pivot forces might act in terms of the radial and tangential direction. Now, the math will prove out what happens. We're just going to take a guess. Now, I know that there's got to be some component along the tangent here that holds this thing up, otherwise the bar would go down. So I'm going to say that the tangential component here, and I'll just call that F pivot T, is going to act upwards to counteract the fact that the bar is going to try and just translate down if that pivot was not there. And just for lack of anything better, I'm just going to put FR here, okay? Or F pivot R here. And we'll see why that doesn't matter. So if I do a sum of forces in the tangential direction, that's going to equal the mass times the acceleration of the center of mass tangentially. So what do we have there? Well, let's call that positive along the tangential axis, and we'll call radially inwards positive along the radial axis for this entire problem. Now I know r hat formally is outwards is positive, but just for sake of argument, we know the acceleration along the radius is going to act inwards, so we're just going to change the axis because it doesn't matter here. So therefore, a positive fg minus an FPT would equal m times the acceleration of the center of mass tangentially. Now, luckily, in an earlier video, we found that. So I'm just going to flash that in here, that we found that the acceleration of the center of mass at that point is going to equal 3/4 g, right? Because we did that torque analysis here in order to prove that. So I'm going to put that in here, 3/4 g, and then we can solve. So mg minus fpt is equal to 3/4 mg. Okay, fpt is equal to 1/4 mg. There I go. And the fact that this came out positive means I guessed correctly in terms of my direction of force, and we're good to go. Sum of forces radially is equal to m a com r. So inwards I have that as positive. FPR is equal to m, and then this is the radial acceleration. No, it's a centripetal acceleration. Vt of the center of mass squared over r. Now, at this position, there's our starting position. That's going to go to 0, and so the component of FPR there is equal to 0. There is no radial component to that, and there I go. So if I want to translate this into x and y, I can say the force of the pivot here is 1/4 mg j hat, right? Because it's upwards. And there is no I hat, because the I hat here would be the r. So that's how we do this. So let's look at a couple other points and see how this goes, right? Next, down here. So we know that it's swung from this position down to here. Once again, I'm going to draw on the forces. There's my FG. I'm going to take a guess just to balance it out. But notice this is the radial direction here. So FPR, I'm going to have going that way. And the center of mass is moving that way, so I'm just going to draw it in. F tangential, P tangential. And we'll start with that one. Sum of the forces tangentially is equal to M com tangential. And so if I look at that, that's just going to be FPT is equal to M A com tangential at that point. Now, here's the thing. What is the tangential acceleration at that point? Well, let's go back to some of our earlier analysis where we looked at generically what was happening at that intermediary point. Boom, right here. Okay? So we said that the alpha, and therefore this was related to A tangential by being R alpha, was this expression. When the object is entirely vertical like that, theta is pi over 2. Cosine of pi over 2 is 0. So that means that the tangential acceleration at this point is equal to 0. Now that should make sense because gravity is the reason why this thing's accelerating tangentially, but at this position, gravity is not acting tangentially anymore, so you don't have to worry about what's going on tangentially there. But if I do sum of the forces radially is equal to M A com radial, I've got FPR minus FG, because remember inwards is positive, is equal to MV com squared over R. So let's plug in what we know. FPR minus MG is equal to M V com. Well, we know what V com of the center of mass is at the end of the problem because we solved for that in an earlier problem. Let me remind you, V com was the square root of 3/4 GL. I didn't find all that stuff for giggles before, right? So this is the square root of 3/4 GL squared all over. Well, here, R, that's got to be to the center of mass, so that's L over 2 in this perspective. So FPR minus MG, we'll move that over later, is equal to M 3/4 GL all over L over 2. Let's cancel some stuff out, the L and the L, this 2 and that 2. And so this just becomes FPR is equal to, I have 3/2 mg and mg, so 5/2 mg. So putting that together then, FP at this point would be once again in the j hat direction, which is actually in the r hat direction here, but we're not going to be too picky about that. So half mg, and it is upwards, so j hat, there is no I hat term to this. This gets a little bit more difficult when we look at the intermediary position. Okay, but luckily we've actually already done some prep work for this. All right, so there we go. Theta. Now, here's the thing. I have a force acting not along our axes, because our axes here are tangential and radial. So I'm going to draw in an FG tangential and an FG radial. And let's look and see where this angle belongs. That angle here is the same as that angle there, which means it's this angle here, right? Because initially, oh no, sorry. It's this here. How do I know? Because no, I was right initially. It is this angle here, because initially the tangential is the same thing as FG, and as theta increases, this is going to keep getting bigger, okay? Or just coordinate geometry, theta, theta, 90 minus theta, theta. Okay, sorry. So there we go. So what does that mean for us? Let's take a guess as to the direction of these. I think we should guess our tangential going opposite our FG, because that seems to make sense, FPT, and once again, FPR. Because remember, the pivot is trying to hold it in place, so it makes sense that it's kind of like opposing gravity in each of those. So I have some of the forces in the radial direction, or the tangential we're doing first, is equal to M A com tangential. So tangentially it looks like, once again, we said that direction was tangentially positive. FGT minus FPT is equal to M A tangential, which is alpha R, right? So I'd have to know alpha at that point. Thankfully, I know that. So G tangential is mg, and we would look at this and say mg cos theta minus fpt is equal to m. Alpha we found at the intermediary point was just 3 halves g over L cosine theta. Thankfully, cosine and cosine are going to match up nicely, and we know that r is L over 2, because that's how far it is from the center of mass is from the axis of rotation. So we can just clean this up now. FPT, actually let's just clean this up first. I've got a 3/4 here, so that's just going to be a 1/4. So 1/4 mg cosine theta, and that's good because it's going to have the right units of newtons, and then with that factor about where you are at that point. And then sum of the forces radially is equal to M A com radial, and so that's going to be, in this case, FPR minus FGR is equal to M A com, which is V com squared over R. Let's put in what we know. FPR minus mg sine of theta at that point is equal to m. We saw that the generic term at any given point along the swing was 3g over L sine of theta, quantity squared, and that's L over 2. So putting that together, FPR is equal to, add that to the other side, mg sine theta plus, and this just becomes a bit of a mess, but what does that become? The L's go away, the square, it becomes 3 halves g sine theta times m, or 5 halves mg sine theta. Oh, that's actually not a big surprise, because if you think about what happens when theta goes to 0, we essentially get, or when theta is equal to 0, we essentially get what we got originally, because at theta 0, this is the only term that survives. That term goes away. Boom, that's exactly what we got here. And when theta is equal to 90, then this term goes away, and we're just left with 5 halves mg, which is exactly what we found there. So it all seems to gel. So The long and the short of it is this is a much harder problem, but it requires us to understand exactly what Newton's second law is asking us to do and acknowledging the fact about how things are changing throughout the motion. And that, my friends, is the swinging bar problem.